So I want to thank you all for coming to our fourth lecture of a new series of radio astronomy talks. We are fortunate to have George Halburn, the late George Halburn, who provided the funding and the vision to really run this series for this academic year. And we've also been supported by Sierra, the College of Arts and Sciences, and the Department of Physics and Astronomy for additional support. Today we are pleased to have Ken Kellermann from the National Radio Astronomy Observatory to speak about the history of radio astronomy. A bit of background. Ken grew up in New York City, went to MIT, and then went to Caltech. He received his PhD in 1963 after... Okay, sorry. Okay, I won't say. Somewhere. After 4 years, and should be a lesson some students here. Then he went to Australia for a postdoc for a couple of years before returning to National Radio Astronomy Observatory. He was a director of Max Planck Institute for Radio Astronomy in Bonn for 2 years, 1977 to 1979. And he has many awards and honors, and to list them all here. Here are some examples: Eastman Kodak Prize, H.B. Warner Prize, Rumford Medal, Benjamin J. Gould Prize, a Fellow of the American Academy of Arts and Sciences, a Fellow of the American Philosophical Society, a foreign member of the Russian Academy of Sciences, Honorary Groth-Reber Gold Medal, the Bruce Gold Medal, and lastly, he's been a member of the National Academy of Sciences since 1975. He's currently a senior scientist at the National Radio Astronomy Observatory. He works on the study of radio galaxies, quasars, cosmology, and the development of new instrumentation in radio astronomy. More recently, he's been interested in the history of radio astronomy. In fact, I believe he's going to write a book about that. And today, he's going to talk about serendipitous discoveries in radio astronomy. And lastly, we have pizza at the end of the hour, so stick around.
Okay, thanks very much, Farid. The last half century or century, I think, as we all know, has seen really dramatic changes in astronomy, and I think this has largely been due, certainly in no small part, due to the discoveries that were made in radio astronomy, mostly accidental, as I'll describe, or serendipitous. And I'd like to discuss some of these discoveries, the facilities that were used to make these discoveries, and then contemplate at the end a little bit about some of the lessons that we might have learned from what's happened over the past 80 years or so. So I think everybody learned in kindergarten, maybe the first grade, about how you're supposed to do science. You have an idea, you do an experiment, you get some results, you analyze it, you draw conclusions, and you write a paper. But I think we all know that's not really the way it works in practice. I think the road to discovery is often very much more complex and contains a lot of twists and turns, false turns. And this is especially true in astronomy, because astronomy is an observational science. We can't do experiments. We can only observe. And I think this is well described by our former Secretary of Energy, Stephen Chu, who was Secretary until 2 years ago. Also has a Nobel Prize in Physics in 1997. He was also my student at NRAO about 40 years ago, so maybe we taught him something. But he said if you're the first person to look under a rock with a new set of tools, you don't even have to be that smart to discover something new. And that's certainly that new tool has been radio astronomy. Until the 1930s, all we knew about the universe came from the very narrow optical window. The high energy, ultraviolet, for the most part, X-rays, gamma rays are, of course, obscured by the atmosphere, and we didn't know anything about the radio waves. That all changed in 1933 with the discovery by Carl Jansky of cosmic radio emission, which opened up the radio spectrum, which runs from roughly 1 millimeter to, say, 100 or a few hundred meters. It's a factor of 10 to the 5. So it's a huge fraction of the of the electromagnetic spectrum, factor of 10 to the 5, compared with only a factor of 2 for the optical window. And of course, once we got into the space age with X-ray and gamma ray observatories, we had another tool. But radio astronomy was the first tool outside the classical optical spectrum, so it's not surprising that that's where a lot of the new discoveries occurred. So it all started in Bell Labs in New Jersey in 1932. Carl Jansky had just gotten his degree in electrical engineering at the University of Wisconsin in physics. There weren't many jobs for physicists at the time, and he applied for a job as an engineer at the Bell telephone company, AT&T and Bell Labs in New York City. And he had a chronic liver ailment, and Bell Labs didn't want to deal with somebody who was going to be ill, and they had to pay his medical expenses. And in those days, you could just reject somebody because he had a chronic illness. You can't do that anymore, of course. But he had an older brother, Curtis, who was a big shot in the radio engineering community. He was president of the Institute of Radio Engineers, and he pulled some strings and talked Bell Labs into giving Carl a job after all. And because of his illness, he instead of having him work in New York City with all its pollution even back then, they sent him to the lab in rural New Jersey. And that, as we see, would essentially change the course of astronomy. At that time, the telephone company had just initiated transatlantic telephone communication. It was by shortwave radio. There were no cables or certainly no satellites. It was by shortwave radio, which was erratic. It was a lot of interference, noises, and it was expensive. It cost $75 for a 3-minute call between New York and London, and people weren't getting their money's worth, so to speak. And Carl was given the job of finding out the source of the shortwave interference to the telephone communications. And after some months of work, he isolated three sources of the radio noise. One was from local thunderstorms, just the kind of thing you hear in your car radio. If there's a lightning storm, you hear static crashes. The second was distant thunderstorms. I should have gone back. He had built this rotating array, which rotated around every 15 minutes. It was highly directional, so it could pinpoint the direction of the radio noise. So one was the local thunderstorms. The second were distant thunderstorms that would last for a few hours off in some direction. And looking at meteorological records, he would find that there was a thunderstorm a few hundred miles away, and that was producing radio noise. But the third source of interference was what he referred to as a steady hiss. And instead of being fixed in a direction on the ground, as the Earth rotated through the day, the direction changed, and he correctly realized it was celestial. At first he thought it was due to the sun, but as the sun moved across the sky at a different rate, he properly concluded that the radio hiss was coming from the Milky Way. So that was a dramatic discovery. Remember, this is 1933. People weren't used, they didn't have cell phones and weren't used to radio broadcasting had just started. And so these radio things were a bit new, a bit exotic, and this had a big impact. I mean, telephone company broadcast the radio noise over the NBC radio network. The New York Times had a front page report. This is the front page of the New York Times from May the 5th, 1933, and they ran this article: "New radio waves traced to the center of the galaxy, center of the Milky Way." And as I said, this caused a lot of public and popular interest, but didn't make much of an impression in astronomy. Astronomers at the time were busy taking photographic plates and measuring the position of stars and the planets, and typical astronomer knew nothing about electronics or radio, and it really had no scientific impact. Unfortunately, and it didn't have much of an impact at the telephone company. Now they knew where the interference was coming from. They said, thank you. Jansky was assigned to other work, and he spent the rest of his career doing noise research at Bell Labs. And during the Second World War, he worked on submarine detection. He ultimately died of his disease in 1950, at just the age of 45, before radio astronomy was really widely appreciated. I think if he had lived longer, he almost surely would have been recognized with a Nobel Prize. And so I said it had no real impact to the scientific community. And for the next 10 years, there was only one person in the whole world that really followed up on this, and that was Grote Reber. Reber had just lived in Wheaton, Illinois, not far from here. He had just graduated from college with a degree in electrical engineering. He was a radio ham. He was looking for something new and exciting to do. He heard about Jansky's reports and heard the news broadcast and so on. And he wrote to Jansky asking for a job, but by this time Jansky had already been transferred to do other work. He wrote to, or he went to Yerkes Observatory at the University of Chicago and he asked what they were doing about this, and they said, well, nothing, we're busy with other things. He wrote to a few other places, Harvard, and they all said, yeah, it's interesting, but we're busy. And so I interviewed him about 20 years ago, and in his own words, this is his reaction as he described it. Whoops, that should play. Let's try this. I had an audio recording that played earlier. Anyway, he said the astronomers were afraid of it because they didn't know anything about radio. The radio people weren't interested because it was so faint it didn't even constitute an interference. So nobody was going to do anything. So all right, if nobody was going to do anything, maybe I should do something. So I consulted with myself. He was very confident and decided to build a dish. And he built this 32-foot dish in his backyard at Wheaton. He took off the summer from work in 1937. And it, by himself, with just the help of a few neighbors for some of the heavy lifting, he built this large parabolic dish, which is by far the largest parabolic dish that had been in use and remained the largest for another 20 years or so. He was a good physicist. He understood radiation laws, and he knew if the hotter things were, the higher the intensity of the radiation, and if you went to a higher frequency, the radiation would increase. He knew the Rayleigh-Jeans radiation law. And so he built his equipment to observe at the highest frequency that was then technically possible, which was about 3 gigahertz or 10 centimeters, and he didn't detect anything. It was very surprising because this should have been many orders of magnitude brighter at that wavelength than Jansky, who was observing at 15 meters. But he went back and rebuilt his equipment to work at 400 megahertz, 75 centimeters. Still didn't detect anything. And finally, he built a third set of equipment at 2-meter wavelength, 160 megahertz, and there he detected the radiation from the Milky Way, and he made the important discovery or realization that the cosmic radio emission was what we now call non-thermal. That is, the radiation decreases with increasing frequency rather than increasing as it would if it was a thermal source. And we now understand that this is due to synchrotron radiation from relativistic electrons in the galactic magnetic field. He went on to make this map of the Milky Way, which, as I said, he realized was non-thermal radiation. He recognized the bright radio source at the center of the galaxy. He recognized 2 other bright regions, one of which we now understand is the radio galaxy Cygnus A, and that's a modern image, not one that Reber had. It's a VLA image. And he also isolated this bright source in the northern hemisphere which we now understand is the supernova remnant known as Cassiopeia, which was observed as a supernova in, I think, about 300 years ago. He also tried to observe the sun and found the sun was surprisingly bright. It's a simple calculation. You know, the sun's, every astronomer knows the sun's 5,000 or 6,000 degrees. You could calculate what the radio emission should be from a 5,000 degree object an astronomical unit away. And he found something that's about 1 million times stronger. That worried him because, well, he already knew that he already had trouble getting some of his work published, and he was afraid that if he publishes that the sun is 1 million or 10 million degrees, he's going to have trouble with the referees. So he expressed the value in these obscure units, 10 of watts per square centimeter per circular degree, and he figured the astronomy referees wouldn't understand that, and indeed they didn't. And then later on, when he was demonstrating his equipment to some visitors, his equipment just went off scale, and he had discovered what we now call solar storms, solar radio bursts, and he recognized that these would occur at the time of other solar activity recognized from sunspot activity. And he published that in the Astrophysical Journal. Well, it turns out that wasn't the first discovery of solar radio emission. During the Second World War, the British had built a radar chain along the south coast to detect incoming German aircraft, and they were having trouble with the radar noise and interference. Radar, of course, sends out pulses, and they were getting signals back even when they weren't sending out the radar transmissions. They thought it was due to that Germany had developed some sort of jamming mechanism. And so James Stanley Hay was assigned to find out the source of the radio interference, and he quickly realized that it was occurring at the time of sunspot activity, and he correctly concluded that the region of the sunspots was causing radio emission. Similarly, in the South Pacific, on Norfolk Island between Australia and New Zealand, Elizabeth Alexander was also studying radar data and recognized that she was getting interference at the time of solar activity. And even back at Bell Labs, George Southworth, who had invented and developed the first waveguide, turned his equipment toward the sun in 1942 and easily detected radio noise from the sun. But all this was during the Second World War. It was all classified, wasn't declassified till after the war, and so it was Grote Reber that had the first publications on radio emission from the sun.
Did he have a day job?
Yes, he worked here in Chicago, well, not here in Chicago, designing radio receivers. He commuted from home by train, an hour each way. I went out there a few years ago. It still takes an hour to get out to Wheaton by train. He worked during the day. He came home, had dinner. He could only work at night because of interference from cars, even back then. And he would have dinner, go to sleep, wake up midnight or so, work through the night, then go off to work in the morning, and kept this up for years. Yeah, there was no chart recorders and certainly no computer recording at the time. And every minute he had to write down the output of the meter on his radio telescope. It was very laborious. Anyway, after the war, a number of radio scientists, both in Australia, primarily in Australia and the UK, used a variety of war surplus radar equipment plus their own ingenuity to continue this work. And ironically, even though the early work had been started in the United States by Jansky and then Reber, there wasn't much follow-up in the U.S. for a long time, mostly in the UK and Australia. They detected, in addition to the galactic radiation, numerous, what they were called at the time, discrete radio sources. The resolution was poor. It was only a few tens of degrees, but they were called radio stars. I mean, Jansky and Reber had discovered radio emission from the galaxy. The galaxy is made up of stars, and so they concluded that these bright radio sources were so-called radio stars. In 1949, though, the first of these discrete radio sources was identified with an optical counterpart. It was getting a good position of the radio source. John Bolton, Gordon Stanley, and Bruce Slee used this equipment overlooking, it was at Sydney Harbor overlooking the Pacific Ocean, and they measured an accurate position of one of the radio sources and realized that it was associated with the Crab Nebula. This is the first time that a radio source was associated with a known optical object. And the Crab Nebula, of course, was the remnants of a supernova that the Chinese observed back in, I think, 1052 or something. And so finally, this got the attention of the traditional optical astronomy community, something that the radio source that was identified was something that what they knew about. And then they also identified two other radio sources with what were known galaxies, NGC 5128 and M87, both known for a long time as peculiar galaxies. M87 has this peculiar jet, NGC 5128, this dust lane. Well, the Crab Nebula already is about a kiloparsec away, and you take the observed radio emission on the Earth and calculate what the luminosity was, and it was fantastic, 10 to the 25 watts or something. These two galaxies are a factor of 1,000 further away, which means they're a factor of a million more luminous, and that was just unacceptable. To have that powerful a radio emission, and they just couldn't accept that. They were all radio engineers or radio scientists, didn't know much about astronomy, but thought they knew something about astronomy. And they said, well, you can't really see any stars in these objects, so they can't be galaxies. They must be galactic objects. And so when they published their result, the name of the paper in Nature was Positions of Three Discrete Sources of Galactic, not extragalactic, but galactic radio frequency radiation. Fortunately, people, I guess, have forgotten exactly what they said in their paper, but this paper was given the credit for the first discovery of what we now call radio galaxies. A few years later, Cygnus A was identified first by Bernie Mills in 1951 in Australia, and he sent a letter to Minkowski at Mount Palomar and said, I think I've identified a radio source with this very faint galaxy. And Minkowski said, no, that galaxy is too far away, and the radio source would be too luminous. It can't be real. And it wasn't until 3 years later that both Australian and British observations really pinpointed the position, and it did turn out to be that faint galaxy at a redshift of what was then considered to be large of 0.05. And Minkowski, that was published in 1954 by Botta and Minkowski, and they acknowledged that years earlier Bernie Mills had made this identification, which they didn't accept at the time. The United States, except for the follow-up optical work, wasn't, as I said, wasn't playing much of a role, and people began to realize this is an exciting field and maybe the U.S. should get involved. And Caltech invited John Bolton to come from Australia and work with the people at Palomar to build a radio telescope to measure accurate positions, which they then used to identify with radio galaxies. And over the Owens Valley Interferometer went into operation in 1960, and over the course of just a few months, there were many new radio galaxies that were identified and redshifts measured. And in the 3C295, which is one of the brightest sources in the sky, was identified by Minkowski, and the redshift measured on his last night at the Palomar 200 inch just before he retired. 3C295 is also a double source, just like Cygnus A. There's a redshift of about 0.5. That is, it's about 10 times further than Cygnus A, and it's also 10 times smaller. And so the idea grew that if you want to observe very distant radio sources, we should look for ones that are very small, since they're the ones that are most likely to be the most distant and would have the highest redshifts. And in early 1960, John Bolton, who is now working at Caltech, and Tom Matthews identified what they were looking for very small radio sources. 3C48 was unresolved. That's the image of 3C48. And it appeared to be a star, not a radio galaxy, but just a star. It was unresolved, less than a second of arc. It had a very peculiar spectrum that, unlike any star, was very blue, had lots of emission lines that nobody could recognize, and it was variable. It varied certainly from night to night and even within a night. And so it was very strong evidence that it was a star and not a galaxy. John Bolton, who had no real background in stellar spectroscopy, looked at the spectrum that others had taken, and he said, it's not a star. And he wrote this. It's not a star, and measurements of the spectrum indicate that it has a redshift of 0.367, and the absolute magnitude is very bright, minus 24, which is 2 magnitudes or a factor of 10 brighter than any known galaxy. Jesse Greenstein, who had taken the spectrum, was an expert in stellar spectroscopy, said no, if you apply that redshift to the emission lines and take the rest wavelengths, they don't quite line up with laboratory measurements, and it really is a galactic star and not a high redshift object. Shortly after that, Bolton returned to Australia to build the Parkes 210-foot radio telescope, which he spent the next 3 years working on. Alan Sandage gave a late paper at the 1960 AAS meeting in New York, and the title was "The First Radio Star." There's no publications at that time of late papers from the AAS meetings, but a few months later there was an article in Sky and Telescope which said there was a remote possibility that 3C48 might be a distant galaxy, but general agreement that it's a nearby star. I tried to find the records from that AAS meeting, and it's been lost. All the meetings before that are available. All the meetings after that are available. And over the next couple of years, there were 3 or 4 more radio stars that were identified, and also lots of radio galaxies. Jesse Greenstein spent a couple of years writing a very elaborate paper on 3C48. He described the spectrum as due to highly ionized rare earth elements. And he said it was the remains of a supernova. His paper was accepted by the APJ. One very short paragraph, he mentions that except for 0.367, same value that Bolton had discussed, no redshift explains the lines at a single ionization. It is not an extragalactic nebula. Tom Matthews and Sandage also wrote a paper about 3C48 as a radio star, and they said there's no plausible combination of redshifted emission lines. So that all changed in 1962 when 3C273 was occulted by the moon in Australia. Because we know exactly where the moon is at any time, and so by measuring the time that a radio source disappears behind the moon or appears on the other side, you can get the exact position. John Bolton had just finished the construction of the Parkes telescope and oversaw the activity. Cyril Hazard was the principal investigator. But you see here tracing 273 was a double radio source. It was known to be a double radio source from other work, and so there hadn't been much interest in trying to observe it because it was thought not to be so far away. But you see the first component coming out, and then the second component, and the second component is so small you even see a diffraction pattern. Meanwhile, the Caltech interferometer had measured a position good to an accuracy of 8 arc seconds, but somehow that got misidentified with a faint galaxy that Schmidt tried to get a spectrum of in early 1962. But the first occultation had good data. It was in August of 1962. A few weeks after that, John Bolton sent a letter, was writing to Martin Schmidt about other things, and he mentions at the end of the letter the position of 3C273 is such and such. And Schmidt took, this was in August. 3C273 is close to the sun at that time, so Schmidt had to wait till December. He actually got to observe between Christmas and New Year's on December 29th. And that's the image of 3C273, the bright star, and what he thought at the time was just an edge-on galaxy. But the radio positions from the occultations are out here, about half a minute of arc away. And so you often read in the literature that the Parkes occultation and the accurate position from the occultation, which in principle was good to a second of arc, or better than a second of arc, led to the identification. In fact, it didn't. The position was way off. But it was close enough that this was too faint to get a spectrum, so Schmidt took a spectrum of this anyway. And again, he found something that had a number of emission lines. This is December 29th. I don't know what he was doing for the next 6 weeks. Maybe he was celebrating the New Year or something, but it wasn't until early February that he finally deduced that this had a redshift of 0.16. Meanwhile, Bolton had sent another letter in late January, but this was after Schmidt had got the spectrum already, with the correct position, one component on the star and one component on the jet. Meanwhile, the Caltech interferometer position all along was right on the stellar object, and that was known to the radio astronomers at Caltech. I was there as a graduate student. It's in my records, but somehow that didn't get communicated properly to the real astronomers on the second floor of the astronomy building. We were all on the first floor. But after Schmidt measured the redshift, he went down the hall, showed it to Greenstein, and they immediately realized that if some of these lines are the same lines that were seen in the 3C48 spectrum, 3C48 has a redshift of 0.37, exactly the value that Bolton had claimed 2 or 3 years earlier. 4 papers were published, one by about the 3C273 occultation by Hazard, Mackey, and Chimmins. Hazard was working for the University of Sydney, and the 210-foot telescope was operated by the CSIRO. Hazard was a guest observer. This is a copy. The paper was submitted by CSIRO, which is a government observatory, and this is a copy of the manuscript as it was submitted. And it's hard to read, but it properly gives Hazard's affiliation as the University of Sydney, and the other two is CSIRO. Written in pencil was the word delete. And so when the paper came out in Nature, it had all 3 authors as CSIRO, and that did not help relations between CSIRO and the university. The second paper was by Schmidt on the redshift, identifying based on these 3 Balmer lines. A third paper by Oak, who had some infrared data, which showed the H alpha line. And then finally a paper by Greenstein and Matthews on 3C48 and identifying that at the redshift of 0.367. Greenstein withdrew his paper, which had already been accepted by the APJ, about 3C48 as a radio star. Matthews and Sandage also had the paper accepted, which was entitled Identification of 3C48 and these other sources with stellar objects. And they got the proofs back, and they just added a section 3C48 as a galaxy. I think we all know the impact of quasars has been huge. They're the most powerful objects in the universe, 100 times the luminosity of a galaxy at a volume maybe the size of the solar system. Led to the recognition of the broad class of objects, which we now refer to as active galactic nuclei, or AGN. Led to the first serious discussions of gravitational energy and gravitational collapse, supermassive black holes, and got the attention not only of the astrophysics community, but physicists who were interested in those areas. Led to the whole series of Texas symposia dealing with gravitational energy. And, of course, it became possible for the first time now to study the universe at very large redshifts and corresponding to very early epochs. Martin Schmidt became famous. Papers on the cover of pictures on the cover of Time magazine. I asked Greenstein once, well, how could you miss this? I mean, the spectrum was right there, and Bolton said it had a redshift, and he admitted that he just couldn't accept the fact that something so luminous could come from such a small volume of space. And he said I had a reputation for being a radical and was afraid to go out on a limb. Meanwhile, John Bolton, who had initially identified 3C48, had measured the redshift, had gone to Parkes, built the Parkes radio telescope, oversaw the occultation observations, brought the results to the attention of Martin Schmidt. He sort of got forgotten in the whole picture. So quasars are all very small, and because they're small, they twinkle or fluctuate in the interplanetary medium, just like stars twinkle in the atmosphere. And Tony Hewish had built a radio telescope specifically to measure the positions of quasars. And he and his graduate student noticed that the small radio sources, particularly when they were near the sun, scintillated or twinkled. And he realized that this was due to the turbulence in the solar wind. And that was, the solar wind had been speculated for a long time, but this was the first direct observation that the solar wind really existed. And so he and his graduate student, Jocelyn Bell, built a new radio telescope. It was just a bunch of dipoles. It cost about $60,000 for the specific purpose of studying these interplanetary scintillations. Most radio telescopes, in order to detect weak signals, typically use averaging times of a few tens of seconds, so you could average over the noise. But because they were looking for these interplanetary scintillations with timescales of the order of a second, they had integration times of only a tenth of a second. And Jocelyn Bell was assigned the job of going through all the chart records, and she noticed that some of the scintillations were periodic. That is, instead of just being random fluctuations, pulses roughly every second. She brought this to the attention of Hewish, her supervisor, and the other senior people at Cambridge, and they said, no, it's interference, get back to your work. But she realized that the time that it would occur every day was shifting by 4 minutes a day, which is, of course, a signal that it was celestial. And she persevered, and she kept pestering her supervisors, and, of course, it finally understood that they had discovered what we now call pulsars, which is a name that was given by a newspaper reporter. So you heard all about pulsars from Scott Ransom. I'm not going to say much more about that, except Tony Hewish did receive a Nobel Prize for the discovery of pulsars. As it turned out, pulsars had really been discovered. I think a lot of you have heard the story of Jocelyn Bell and how she discovered pulsars. But actually, pulsars had been discovered about a year earlier by somebody named Charles Schleicher. At that time, it was during the Cold War, and the United States and Canada had built what was called a ballistic missile early warning system, or the DEW line, which is a series of radar stations across Alaska and Canada, which is supposed to detect incoming Soviet missiles before they, 10 minutes before they reached the United States and did their damage. This is the DEW line station at Clear, Alaska. Schleicher was working, he was a radio technician. He was working at the DEW line station. And of course, radar, again, is pulsed. And he noticed he was getting pulses back without transmitting. And he followed that up. And he was a former Air Force pilot. He knew celestial navigation, celestial mechanics, and he immediately realized these pulses were coming 4 minutes earlier each day. And he understood what that meant, and he worked out the celestial positions. He realized it was coming mostly from places in the galaxy. He took a day off on Saturday. He drove 200 miles to Fairbanks, to the library, went through a radio catalog to see if any of these pulses were coming from any known objects, and he only found one, and that was the Crab Nebula. And even he knew about the Crab Nebula, and he realized that this was important. It was about a year before the Crab Nebula pulsar was discovered at Arecibo. But of course, this was all classified and was only declassified about 10 years ago. Observations by Joe Taylor and Russ Hulse. Pulsars have been important not only for their intrinsic interest in studying physics of neutron stars, but also because they're such accurate clocks. They tell us so much. And Hulse and Taylor, particularly Hulse, down in Arecibo, observing this binary pulsar. And from the timing of the pulses, they realized that, because, we say the planets in the solar system go around the sun, but they don't really. Both the planets and the sun go around a common center of mass. And so the pulsar and its companion revolve around a common center of mass, I think about a 5-hour orbit. And Hulse realized that the timing of the pulses was changing in just a way that would happen if the pulsar was radiating gravitational waves and losing energy. And and of course was the first, and still this is the theoretical prediction. It's not a fit to the data, but a theoretical prediction of the effect of gravitational radiation, and these are the observations. Of course, they were working just for, the first few years here, but that's continued on until now, and is the first and still, I think, the only demonstration of observation of gravity waves. And Hulse and Taylor also got the Nobel Prize for that. More recently, two other radio astronomers were observing a pulsar whose position and velocity seemed to change, in this case due to not one planet, but two planets moving around the common center of mass. And so the pulsar itself is jittering back and forth, and you can see that in the timing. And that was the first detection of extrasolar planets in 1991 or 1992. For a long time, until relatively recently, it was the only detection of an extrasolar planetary system that has more than one planet. Now there are many from various ground and space-based observatories. The cosmic background radiation was perhaps one of the most spectacular discoveries of the last century in astronomy. Bob Wilson and Arno Penzias working at the same Bell Labs as Jansky. And they were also not trying to do radio astronomy. They were testing this horn antenna, which is used to bounce radio signals off a satellite. They had about 3 degrees more noise from their system than they thought they should have. Turns out the cosmic background radiation was predicted by back in 1946 by Gamow and Alpher, and also more recently by two guys in Russia. But nobody seemed to know about those predictions. They spent a lot of time trying to understand their data. They thought it might be coming, noise from New York, but it was isotropic around the sky. They thought it was perhaps due to pigeon droppings in the antenna, so they went in there and cleaned it out. Meanwhile, just 30 miles away at Princeton, Bob Dickey had repredicted that the Big Bang after 14 billion years, after it cooled down, would leave a radiation background of a few degrees. And he and his graduate students were building equipment to detect the cosmic background radiation. But of course, they were beaten out by Penzias and Wilson. They certainly hadn't set out to discover the background radiation, and didn't know about either of these, any of these earlier predictions. This has been followed up. This is a whole new industry. There have been literally thousands of papers written on the cosmic background radiation, started by Penzias and Wilson discovery. The COBE satellite measured the spectrum to great accuracy. The Planck satellite measured the anisotropies to great accuracy. It's resulted in 4 Nobel Prizes: Penzias and Wilson, George Smoot for the COBE observations, and Mather for discovering the small-scale anisotropies in the background radiation. Meanwhile, it turned out that background radiation could have been discovered years earlier, even with equipment from the Second World War. And in fact, Dickey had done an experiment just after the war where he measured the background to be less than 20 degrees, but apparently by 1965 he had forgotten about that. Also, it's a well-known problem to astrophysicists that interstellar cyanogen, the absorption lines corresponded to an excited state of about 2.3 degrees. And it was well known, apparently, at the time. It had been since 1941, and it wasn't clear how the cyanogen molecules got excited. It was thought maybe it was due to collisions, but as we now know, is due to the cosmic background radiation of 2.7 degrees. It also turned out that background radiation had been actually observed a year earlier by somebody else at Bell Labs using somewhat different equipment. And it was published in the Bell Systems Technical Journal, which is not widely read other than by radio engineers. It was marginal. It was 2 plus or minus 1 degree, but nobody noticed it except the 2 Russians who had predicted this. They had a graduate student going through the literature, and he found things that none of the Americans knew about. This paper by Ohm. But his English was a bit marginal, and they misunderstood the paper, and they thought that this excess 2 degrees was due to the atmosphere, whereas actually Ohm explains in his paper that he had corrected for the atmospheric emission, and this was the residual that was left over. So a lot of people missed out on discovering the cosmic background radiation. So far I've been talking about continuum radiation, over a wide range of the radio spectrum. During the Second World War, Van der Hulst predicted that in a hydrogen atom, if the spin in the electron and proton first parallel and then flip over, become anti-parallel, that radiates at the energy released corresponds to a quantum at 1420 megahertz or 21 centimeters. But he said that the existence of this line is speculative because it would require a huge lifetime in the excited state. Doc Ewan, real name was Harold, was a graduate student at Harvard. He didn't understand the astrophysics well enough to know that it shouldn't be detected. So he and his supervisor, they were electronics people, and so they built this horn antenna, pointed it toward the sky, and he detected the 21 centimeter line, and that became his very, very quick thesis. Van der Hulst also predicted what we now call radio recombination lines. That is, in atomic hydrogen, the very high orbital energy levels, the transition from the n+1 to n level produces a quantum in the radio spectrum. But, Van der Hulst pointed out that these lines would probably be unobservable because to get radiation, the corresponding energy levels are quantum numbers of the order of 100. And the electron and the proton are so far apart that the electron is also seeing external electric fields. And he said that the Stark effect from the external fields would perturb the orbit sufficiently that you wouldn't get discrete transitions. It would all blend out. Well, it turns out that if you have an external electric field, these far out energy levels are so close together that they see essentially the same electric field. And in fact, you do get the discrete transitions. And that was discovered first in Russia only marginally and wasn't believed in the Western world, partly because it was Russia. It was during the Cold War, and was confirmed in the U.S. in 1965. There's also the molecules. Up until 1964, there was only one atomic line, one spectral line known in the radio spectrum, and that was the hydrogen line. Towns and Shklovsky had predicted that there'd be other molecules would have transitions in the radio spectrum, like ammonia and formaldehyde and carbon monoxide, and they were all discovered in the late 1960s, and now there are more than 4,000 lines that have been detected throughout the spectrum associated with almost 200 different molecules. In particular, the OH transition turned out to be very mysterious, is very narrow band, very strong, and fluctuated with time in time scales of days, which is surprising for a large molecular cloud. And it was initially given the name, and the relative abundance in different transitions was anomalous, and it was given the name Mysterium, which later turned out to be that the so-called Mysterium is due to a maser effect, a stimulated emission. Molecules get excited in upper state, and the transitions are all in the radio spectrum. We now know about the water vapor masers, silicon monoxide masers, and methanol masers. This is an example of a radio spectrum from the Orion Nebula, just between 70 and 90 megahertz. There's hundreds of lines here. I'm not going to say much about the solar system. We know how hot the sun is. We know how far the planets are. You should be able to calculate what the temperature is of each planet and what the corresponding thermal radio emission should be. I'll just say, aside from Mars, every planet is anomalous and has strong radio emission, including radio bursts from Jupiter that can be detected just with simple shortwave radio equipment, and also the radiation belts from Jupiter, analogous to the Van Allen belts. But I want to spend the last few minutes on. So I've been talking about how things happen in astronomical or scientific discoveries. They don't always work the way the textbooks say, and it turns out that's partly true also when it comes to building large equipment. I think we've all been brainwashed into If you want to spend a lot of money to build a big radio telescope, you have to write a proposal, you have to get a lot of people behind it, you have to have conferences. You submit it to the NSF or somewhere, and they have peer review, and they have committees. And this literally takes years. In practice, it hasn't always worked that way. The Arecibo telescope, which talked about, made a number of major discoveries. It's the largest filled aperture radio telescope in the world. Wasn't built for radio astronomy. It was built by Bill Gordon at Cornell to do ionospheric physics using radar to bounce radio signals off the ionosphere. And he calculated that he needed a 1,000-foot antenna to detect the reflected radio signals. Turns out he made a mistake. And he raised money from the Air Force to build the antenna. The Air Force was interested in understanding the ionosphere because, again, Soviet missiles coming in might leave trails. And they really wanted to understand how the ionosphere worked. And it turns out that Gordon had made a mistake, and really a 100-foot antenna would be good enough to do his experiment. But by that time, people had become enthused about a 1,000-foot antenna. You could also see radar from the planets. And he had already got the money from the Air Force, so he built the Arecibo telescope, which has had a glorious history in the radio astronomy. I discussed some of the gravitational radiations in the planets and hydrogen and pulsars. Similarly, at Jodrell Bank, before the Second World War, in the late 1930s, Sir Bernard Lovell had calculated that you could detect radar returns from the ionization trails of cosmic rays, and he was interested in studying cosmic rays. And he published a paper on this, and immediately it was shown to be wrong by somebody that these ionization trails would immediately recombine, and you'd never be able to detect the echoes. Well, then the Second World War came, some years after the war, Reconstruction and everything, and by 1950 or so, he had either forgotten about this paper, which showed that he was wrong, or just chose to ignore it, and he built the Jodrell Bank 250-foot telescope to study cosmic ray echoes. And I think the most spectacular story, though, comes from the Green Bank telescope. For decades, U.S. radio astronomers had wanted to build a large, fully steerable radio telescope. And it was even in the plan for the National Radio Astronomy Observatory at Green Bank. And it had been recommended every time by one of the decade reviews of astronomy. But it was never the first priority. So the first decade review gave priority to the VLA that got built. Then came the VLBA. And then came a millimeter antenna. And then came ALMA. So the large, fully steerable telescope never got built in the United States. And in 1960, when Green Bank was building the 140-foot telescope, they ran into a lot of technical issues, cost overruns and delays. And so the staff got together and designed and built within a year, at a cost of under $1 million, a 300-foot radio telescope, which was only a transit telescope, and it only moved about 60 degrees in elevation, didn't even cover the full range of elevations. It had just a chicken wire surface, so it was very cheap, but only worked at relatively long wavelengths because of the imprecise surface. And over the years, it was thought, that would be used for a few years until we got to build a fully steerable high-frequency antenna. But that never, as I said, that never got built. Various improvements went into the 300-foot over the years, and it made a lot of important discoveries, including, in fact, the Crab Nebula pulsar. But by 1987, the NSF was running out of money to operate radio telescopes, and they convened a committee to look at all the radio telescopes in the United States, the ones operated by NRAO, the ones operated at the universities, to see which could be closed down so they could save money. That was a good committee, of course, and they said, no, they're all important, but they did recognize they had to do something. And they classified the radio telescopes in three categories. There was category A, that absolutely essential, has to be operated under any circumstances, and that was, I think that included the VLA and the VLBA. Category B was really important. It should be operated, if at all possible, and that included the 140-foot and Arecibo and a few others. And then there's category C, that, well, they had done good work, but now is the time to to move on. And so the Serendipitous was scheduled for closure. And all the other radio telescopes in Category C were closed. This photograph was taken on November 17th, and that night, so-called gusset plate, which holds together a number of the members, cracked. And so those members, which were supporting part of the backup structure, gave way, and that caused some surrounding members to crack and collapse, and that spread to a wider area, and within a few minutes, that was all that was left of the 300-foot telescope. This picture taken the following morning. Well, it was a mess. Well, it was scheduled to be closed, so all right, you have to clean up the mess and move on. But it wasn't that simple. The news media got a hold of this. They sent out the helicopters from the Washington TV stations. They took pictures. It was on the national news and everything. At the supermarket checkout stands where you see the tabloids, there were articles saying that the telescope had been zapped by aliens because we were listening in on their communications. But even the serious newspapers, the Washington Post said that the collapse was going to hinder astronomy for a long term. The New York Times said it set back astronomical research by years. And the Philadelphia Inquirer, a big setback to the international search for extraterrestrial life. All this for a telescope that was scheduled to be closed. And the NSF was prepared to pay somebody to come out and clean up the mess and move on. Except for the good Senator Byrd from West Virginia, who had been a patron, shall we say, of NRAO and Green Bank for many years. And he was chair of the Appropriations Committee at the NSF. And he immediately summoned the NSF director into his office and asked, what are you going to do to rebuild the Green Bank telescope? Eric Bloch was the NSF director. Bloch was the first NSF director that didn't have a background in science, physics. He was an engineer. In fact, he had come from IBM, and in fact, he had designed the IBM 360 computer system, which see some gray hairs out there. that was the thing, not only in science, but also in banking. It was a major computing system. It existed in several models, so it could do almost anything. And Byrd asked Bloch, well, what are you going to do about this? And Byrd explained that, well, we have a system of peer review and everything, and we don't want to build a telescope in Green Bank. We have some other projects that we want to do. And Byrd got rather upset and said, I want this new radio telescope in Green Bank. And Bloch went on and tried to explain that, well, we need a proposal, and then we send it out for review, and then we compare it with other proposals, and we have a committee, and so on and so forth. And by this time, Byrd was really getting furious. And the junior senator from West Virginia was Jay Rockefeller at the time. And apparently he took Bloch aside and said, Mr. Bloch, the senator chairs the subcommittee of the Senate that allocates funds for the NSF every year. Maybe you ought to give this some consideration. This is a long story, but to make it short, every year, at the end of the year, the U.S. Congress passes what's called an Emergency Supplemental Appropriations Act. And that's to cover the cost of various emergencies, disasters that have happened over the previous year. Hurricanes, floods, fires, earthquakes, mudslides, and so on. Now you think with a logical system, you know that statistically some of these things are going to happen every year, and you could allocate the money at the beginning of the year. But by doing it at the end of the year, after the whole budget process is over, somehow this is a way to fund something that doesn't count against the budget ceiling. So the 1989 Emergency Supplemental Appropriations Act included $75 million spaced over 2 years to build a new radio telescope in Green Bank. I think it was one of the first times that the funding was ahead of the design, and it took the better part of 10 years to design and build the Green Bank telescope, which is in fact the largest fully steerable telescope in the world. It's most sensitive, and it works over an enormous range of wavelengths. So let me, just in the minute or two I have left, to just make some comments on what we've learned from these activities. I think important discoveries require both the right people, smart people, also some luck, being in the right place at the right time, and recognizing what's important, what's new scientifically, and what might just be an instrumental effect. You have to believe your data, but you also have to get more observations or more studies to confirm it, as Carl Sagan said once. And I think that comes back even, Laplace said it earlier. Extraordinary claims require extraordinary evidence. But one shouldn't be, having that evidence, as I showed some of our people did, one shouldn't be afraid to claim new discoveries. Often in proposing for observing time, or proposing to build a new instrument, or trying to get a grant, referees want so much explanation of what you're going to find that if you knew all that, you wouldn't need to make the observations or get the grant. And if you just want to say, I got a new tool and I want to see what I can discover, of course that doesn't get anywhere. But in fact, that's exactly the technique that's led to all these discoveries. So the aficionados, they may want to do a study just to see what they see, but you write the proposal in such a way as to sound like you know what you're doing and you're testing a model or something. You have to beware of theoreticians. They often think they know more than they do. I didn't mention that we had a proposal at the 140-foot telescope to observe water vapor, and our referees rejected it because they showed that the abundance of water vapor was such that you couldn't detect it with a 140-foot telescope. And in fact, it was because it was measuring simulated emission, thousands of times stronger, and it was detected 6 months later with a small radio telescope at Berkeley. So you have to watch out for theoreticians. And it's important to have good colleagues. I think it's no coincidence that Jansky and Penzias and Wilson were working at the same lab. And there are a lot of smart people there. Claude Shannon, Towns, Nyquist, all famous names, Shockley and Bardeen, who invented the transistor. And also, and I didn't have time to discuss it, everything you read in the textbooks isn't always right. Starting in 1880, the textbooks all said that Mercury rotates around the sun at the same rate. It revolves so that the same side is always facing the sun, which is extremely hot, and the backside is always away from the sun, which is extremely cold. Radio observation showed, in fact, that both sides have the same temperature, which was the first clue that it really rotates. And then 6 months later, radar observations showed that it really rotates. And then the theoreticians came out. It rotates. The orbital period is 88 days, and it rotates in 55. And so it does turn around with respect to the sun. And within weeks, there were papers in Nature by the theoreticians explaining all this. Oh, yes, we understand that. But they didn't understand it until the observations showed it. And finally, I just want to say that I think both in the past and hopefully in the future, the excitement of building new telescopes is not in the old questions that you try to answer, but in the new questions that are raised by the new observations. So thank you very much.
Thank you very much, Ken. We have some time for questions. Go ahead.
Yeah.
So I just can't get over that it took so long for people to follow up on Jansky's discovery. Like, was it just that there was no one who was able to build those kinds of radio telescopes, or
No, well, Reber did in his backyard Wheaton with his own personal funds. I think it was a combination of things. Remember, it was during the Depression. People had other things to think about. So even at Bell Labs, people were on a 4-day work week with a corresponding cut in pay. And so Jansky himself, he knew he had this serious illness. He had a young family. He needed that job. He would have liked to he looked into the university position, but he knew he needed that job at Bell Labs. And so in his case, he wasn't able to follow up. And I think it's hard to put ourselves in the psychology of the era. I mean, we're so attuned now to technical things. I mean, everybody's got a thing in their pocket they can talk around the world with. That wasn't the psychology of the time, especially considering the effect of the Depression. So it wasn't. So I say Reba was working alone, and it wasn't until after the war when a number of the radio scientists who had been developing radar both had developed their personal expertise and also had all the surplus equipment that they could then use for cosmic observations. Now, as it turned out, there's still another 10 years before the U.S. really got involved, and that may have been because during the war, the U.S. wasn't involved until 41. Other countries were involved in 39, and also we were somewhat protected. That is, we weren't being bombed every day, and Britain was under daily attack, and so they had a crash program to develop radar, and electronics was much easier than at meter wavelengths, and so they built that series of equipment that I showed, and after the war they were able to use that to do radio astronomy. The U.S. by agreement between the U.S. and their allies, it was agreed that the U.S. would concentrate on high frequency radar, which had better angular resolution, better localize the planes, because there wasn't an immediate emergency. Well, because of this non-thermal radiation, the radio sources are weak at short wavelengths, and so even after the war, the U.S. equipment really wasn't suitable for cosmic work, and it wasn't until until late 1950s that the U.S. really got going.
You didn't mention Kerr or Westerhalf just because you didn't have time?
You mean as far as the 21 centimeter discovery? Or that's right, yeah. The both in Australia and in Holland, they were building equipment to detect the 21 centimeter line. They had over-designed the equipment in the sense that, for the reasons that Van der Hulst had given in his paper, they thought it would be much weaker than it actually was. So they were designing very elaborate equipment to detect the line. Ewan came along with just a simple horn, detected the line. They realized how strong it was. And in fact, in Holland, they had a fire which burnt down their whole lab. And just within a month or so, they were able to rebuild the equipment, much simpler equipment, and also detect the line. People were real gentlemen in those days. They were all men, but they were gentlemen, not ruthless competitors. And the Dutch and the Australians, Ewan from Harvard waited till the Dutch and the Australians confirmed the result, and they all published simultaneously in the same issue of Nature, rather than rushing off to beat the competition.
A question about Dickey. Could he actually discover the cosmic microwave background radiation if there was no accident in his lab?
Oh, no, I'm not aware of an accident in his lab. They just...
Oh, so there was no accident in his
lab? They were just starting, or only partly along. They just hadn't finished the equipment or hadn't done the observations.
Oh, okay.
And then he heard about the Penzias and Wilson result and went over and looked at it and realized that I think his words were literally, "Boys, we've been scooped."
Maybe I have another follow-up question. Can you speculate why there's so many discoveries being made in the 60s?
I had this, but I knew I wasn't going to have time to discuss it. I tried to understand, what the background for each discovery was, whether they were looking for something else, whether it had been predicted, whether it had been predicted that it wouldn't happen, whether the theory was wrong. There's no simple pattern. Also, so it was during the 60s that we had this new generation of radio telescopes, Greenbank, Parkes, and then the VLA. But that doesn't account for it, because a lot of these discoveries were made with relatively simple equipment. As I said, the cosmic masers was a very simple antenna at Berkeley. Pulsars was just a bunch of wires and poles. Quasars had the 200-inch telescope, but didn't need it. It's 3C273 is a 13th magnitude object. It's been cataloged for over 100 years. Anybody in their backyard could have gone out and done a spectrum of 3C273 if they'd known where to look. Now, some of these things, the radar things, of course, were high-tech things that required the big equipment. The Jupiter radio bursts were discovered with a simple array in Maryland. And the solar, I mean, the solar radio burst you can see on your TV antenna if you still have TV antennas. So it wasn't because of the new generation of large, expensive radio telescopes. One other possibility, I mean, looking at it from a personal side, these early discoveries were made by radio engineers with backgrounds in electronics. The more recent, I mean, modern generation, these people had no training or certainly no academic training in astronomy. The more recent generation of radio astronomers have had strong academic training, mostly with an emphasis on astronomy and astrophysics, with relatively little understanding of the electronics. The generation which I'm proud to be part of, say a second or 2.5 generation, my thesis supervisor was John Bolton, who was a first-generation guy. We had the academic background, got degrees in astronomy, radio astronomy, or astrophysics, but we were also taught by the real guys who really developed the equipment. So maybe we had a bit of, and Bob Wilson was a classmate. So unlike Jansky, I mean, Wilson and Penzias had degrees. They had degrees in physics, but both of their PhD theses were in radio astronomy. So even though they weren't looking for the cosmic background radiation, they were quick to realize what it was and why it was important. So that's one possible explanation of what was special about the 60s.
Was there any bias in the early days in the publishing world about publishing papers in radio astronomy?
Reber had problems because he had no credentials. I mean, at least, these other people worked for Cambridge University, so of course, that automatically gave him credit. No, Reber Jansky published all his work in the Proceedings of the Institute of Radio Engineers. And I mean, you can go back and look at the papers. They're very detailed electronic analysis of the circuits and why the noise was real and so on. Perfect, beautiful papers, but no astrophysics. And he didn't even try to publish in the astronomy journals, but Reber did. And he sent his paper to the Astrophysical Journal, whose offices at the time were at the University of Chicago. Chandrasekhar was the editor, as I mentioned yesterday in a different context. And they didn't know what to make of it. They couldn't find a referee because there was nobody, in the field. But Jesse Greenstein, the one who later went on to start the astrophysics department at Caltech and bring Bolton in to start radio astronomy, he was a postdoc at Yerkes at the time, and he was a radio ham, so he knew something about electronics. And Chandrasekhar sent, first the APJ editor wrote to the IRE asking about Reber's credentials, and they just wrote back and said he's a member of he's paid his dues and he's a member in good standing. So that wasn't good enough. He sent Greenstein down out to Wheaton, which is just a few miles away, to talk to Reber, look at his equipment, and he came back and said he seems to know what he's doing. The equipment seems real, and so they accepted the papers and published. But Reber had some theoretical interpretation, which the journal took out or got him to take out. It was wrong, but and then he published several papers in after 1945. His father had died, and he went to work for the Bureau of Standards in Washington, sold the U.S. government his antenna. I guess it was about 1950, and that was not during only the Cold War, but it was during the McCarthy era, and he was a very independent person. I mean, nobody could tell him what to do, and he couldn't tolerate working for the government and all the things that were going on with the McCarthy hearings. And he apparently went to Hawaii for a vacation and never came back. And he built a radio telescope on Mauna Haleakala in Hawaii. But he realized that the top of mountains isn't a good place for radio telescopes. You get all the interference. He wanted to work at very low frequencies. And he realized there are two places in the world where you can work at low frequencies, where the ionosphere isn't a problem. One was north of Hudson Bay, and the other was Tasmania. And for obvious reasons, he chose Tasmania, and he spent the rest of his life there. But he worked in all sorts of fields, archaeology and biology, but he never made another significant contribution to radio astronomy. That's the other lesson. If you don't do it by the time you're 30, it's too late.
Okay, if there are no other questions, let's thank the speaker again.